Right. So in this demonstration, I have a lens and I have our optic source here. Maybe I'll rotate this just a second so you can see it. Oh my gosh. Let me just do this. I've got our object, and we're going to put our object down here at this end. Oh. We're going to put our object down here at this end of the mirror, at this end of the optics bench. And then notice I've placed a screen here at about 110, something like that. Somewhere in there, right about there. And then the idea is, where do we put this lens such that we get an image? And you can see that there's some images forming there. We'll have to zoom in and out, but we'll do that in a minute. Let's do the calculations first, then we'll come back and do the demonstration. All right, so let's go to the board. And that's just a little bit low. There. All right, so here's the problem that we're looking at. There's all my markers. There's the black marker. There's one. Okay, so we have an object at one end. We have a screen at the other end, and then where are we supposed to put this lens so that we get an image on the screen? And rather than use the numbers, let's try and do everything algebraically so that you get used to solving problems algebraically in case that's on a test. Also, it's handy because then you can have a formula to shove into a computer program or something like that. All right, so let's get into it. Where are we going to place this lens? So let's start with some, if you want to try the problem by yourself, go for it. And then what I'm going to do, the solution is a little bit long. I'm going to give you most of the steps that I think will be the tricky ones and leave out some of the boring algebra just so it fits on the page. But so I'm going to start solving this. I'll give you some hints and then I'll solve it. Okay, 1, 2, 3, here come the hints. Well, the first thing you might do is write down that's always good to have on your paper for an image formation problem, the 1/f equation. And we've seen that this can be rearranged just to solve this for d image or do. In this case, I'm going to just solve it for d image because that's what I did in a previous problem. You could see the algebra, I think, on the first one of this chapter. But it was do f over do minus f. Remember, we moved this to the other side, get a common denominator, and then flip it upside down. So this is one useful equation we might have. The other one is a constraint. We know this total distance is L, all right? And so if the total distance is L, what is the relationship between do and f, right? We can eliminate one of our unknowns by saying L is equal to do plus di. And from there, what do we see? We could see that d image is L minus do. So there's your hints. If you want to try and solve it yourself now, go for it. I'm going to try and show you more hints or just finish the problem in 3, 2, 1. Okay, so you could obviously set these equal to each other. And at this point, I'm just going to do a quick check. What the heck are we trying to find? Where to place the lens? Well, if I know do is literally telling me how far away from the object I should put the lens. So that's a good thing. I know what L is. L is a given. So that's a given. This is not known, not known, not known. F is also given in the problem. So do is the only unknown. I should be able to solve it. If that's the hint you needed, go ahead and pause the video and try to solve it. I'm going to proceed in 3, 2, 1. Okay, let's get rid of these check marks. So now I'm going to cross multiply here and get L minus D0 and D0, or I guess DO for object, not D0, sorry. I'm a bad person. D object. Keep calling it D subscript 0 because O looks like 0. All right, and then what do I want to do? In this case, I'll just FOIL this out. Do I want to write that step? Hopefully you can show that when you FOIL that out, you get the following. I'm skipping several lines of work here, but this part you should be easy. Hopefully. One of the interesting things is notice you'll get a negative DO times negative F, which cancels out this term, right? Because this becomes positive opposite side. So then you get this. Think, how do you solve this? 1, 2, 3, quadratic formula. A is equal to 1, B is equal to negative L, and C is equal to LF. You don't have to have numbers to do the quadratic formula. We can just plug it in. So notice D object is our unknown, L and F are both known. So right, this is like X, and these are just some numbers. So pretend they're numbers. And we're going to get negative L, A is 1, C is LF, and so when I work that out, it's going to be positive L plus or minus the quantity, L squared minus 4LF, all over 2, right? So I know you probably are going to have to pause the video and make sure you can get to that step. Pause the video now and make sure you can get that. I'm going to go ahead and shove in the numbers too, so if you want to go ahead and make sure you could derive this yourself, right? Me writing it down on the board doesn't mean you know it. Make sure you can get there, and then plug in the numbers. I'm going to write down the numbers that, the answers I got when I plugged in numbers in just a second. Okay, so 1, 2, 3, here we go. I got 67.9 centimeters, or 42.1 centimeters. Now wait a second, does that really mean we have 2 places we can put the mirror and have this, the lens and get an image? Absolutely. But will both of them be enlarged? This is where I was sneaky, all right? Only one of those answers is going to give an enlarged image. From experience, I happen to know the following. When the lens is really far away from the object, you get a tiny, tiny image, right? So if the object is really far away, you always get a tiny image, and the image is almost exactly the focal length away. So that would be a diminished one. So we probably want to use the smaller answer here. So by plugging in the numbers, you can kind of think, well, wait a minute, I probably want to use the minus sign, and in fact you do. The negative sign gives the enlarged image. Now, so that's my claim. Why don't we draw a ray diagram really quick? And so in order to have room to draw the ray diagram, I think I have to erase this part of the problem statement. So let's just do it. You can always rewind. So we want an enlarged image, and this is what we're using. So to be clear here, this is 20, 40, 60, 80, 100, and that's 110. All right, our object is 10 centimeters tall. There's 10 centimeters. Yep, looks good. All right, and we're saying put the lens 42 centimeters away. So 42, 10, 20, 30, 40, and 2. So instead of drawing a lens, I'm going to just draw a dotted line, and then I'm going to try to draw the rays in the same order as I recommend. Ray 1, parallel to optic axis. Oops. Hopefully that's parallel. It's a little off. If you don't know where these are, I'm following from page 26. Page 26 has all the ray names and conventions. Is that showing up? It's a little crappy. Let's try a different blue. Looks a little better. All right, and now it has to go out to the focal point. So in parallel to the optic axis, out to the focal point. Well, where is the focal point? 25 centimeters away. So we've got to be a little bit careful here. So there's 10, 20, 5. Oops. And we could do one here. 10, 20, 5. So there's focal point, and there's focal point. All right, so this incoming ray it's going to be inverted. I'm going to, that's all right. We'll just draw a bigger screen. Okay, so that's ray 2. Or whoops, ray 1. Okay, and then ray 2. Towards focal point, refracts parallel to optic axis. And that is, I believe, a red one. So in through the focal point. Out parallel. This is looking good. Okay, it's not perfect, but it's looking pretty good. That's ray 2. Confirm with ray 3. Right through the center, passes through undeflected. Ray 3. It's pretty close. I'm trying my best here. It looks like I bumped it a little bit. Not bad. So notice the ray diagram does confirm it's not exactly right. They never are. It's hard to draw to scale perfectly. Oh, and let's label this one. That's ray 3. And now, is it enlarged? According to this, we expect the image to be right about here. Okay, I'm being a little bit sloppy there on purpose just because there's some spread. Some of the lines don't match up. And we get, oh, well, let's flip the ruler upside down. About 16 centimeters, something like that. All right, and we could actually calculate what the magnification should be, what the image, final image height should be. So let's do that. Magnification is equal to negative di over do, which in this case, think. We know L minus do is equal to di. So we have that calculation. We can do that. 110 minus 42.1, 67.9. All right, and so notice this magnification should be negative 67.9 divided by 42.1, about 1.6. Negative 1.6. And didn't I say it was about 16 centimeters there? That's pretty darn good. Maybe closer to 15, 16, somewhere between 15 and 16. So this is matching up pretty good. Pretty well. All right, and so I guess what I'm saying is height of the image should equal magnification times height of the object, which in this case is negative 16.1 centimeters. So that's our prediction. Now let's go ahead and run this thing and let's look at it. Let's go do the actual experiment and see if that matches reality. Okay, Let me zoom in. Oops, come on. Trying to zoom in as much as possible so you have a chance at actually seeing the image. Oops. All right, I guess that might be about as good as I can do. Right there. All right, so now let me get this set up. Good time to double speed the video, huh? Line this up in here. Trying to get this right. Oops. Got caught on something there. All right, so what I'm doing is I'm trying to line up the face right here at the front. Oops. Like that. That's pretty darn close. It's never going to be perfect, is it? All right, and then right about here, 42, right about there, and we'll see if we see an image on this screen, and the screen is right here at 110. Let me hit some lights. Can you see that? Can I do? And I just got to check the screen on Zoom really quick. Oh yeah, I can see the image there. Do you see that? Okay, this is good. So just trying to prove that it's not just coincidence, I'm going to try to move this out a little bit, and you shouldn't see the image. So we're looking right here for the image, right? Maybe if I just go to this side, I can see. So no image. Image looks pretty sharp right about there. That's 41.5. It looks sharpest. Then it gets weaker. But now let's see. And notice it is enlarged. It's about 16 centimeters, spot on. That's right. Okay. And then what was the other measurement we said? You can see an image at, what was it, 67.9. We see another image forming, but notice, I like to slide it back and forth and gradually work. I ended up getting this at 70, but notice this image is diminished. It's only about 6 centimeters tall. So we see this works out. Hopefully you can see that on the video. Let's call that good.